We have discussed the concept of virtual shorts in circuits which have op amps in negative feedback loops. Now we can do the same for transistors in negative feedback. Okay. I'll take one particular example, which is the voltage controlled voltage source or a source follower, and the same principle applies to all other circuits as well. Okay. Now the incremental picture of the source follower is like this. Just for simplicity, I'll omit the resistance of the input source. This is the load resistance. We have VGS and GM VGS. Okay. Now we know that the output voltage which appears at the source terminal is given by Vi times GMRL by 1 plus GMRL. Okay. This VGS is nothing but Vi minus Vo, and VGS will be 1 by 1 plus GMRL. While discussing the voltage controlled voltage source or the source follower, we said that as GMRL becomes very large, as it tends to infinity, we get an ideal voltage controlled voltage source which gives you V0 equals Vi, that is ideally gain equals 1. Okay. And similarly for other feedback circuits, other control sources, we evaluated that when GM of the transistor becomes very large, when it tends to infinity, the circuit behavior tends to the ideal. Now we can discuss it in terms of VGS. What happens to the incremental VGS when GMRL becomes infinity? As GMRL tends to infinity, VGS becomes 0. VGS tends to 0. That is, there is a virtual short between the gate and source terminals. It's normally not thought of like this. Okay, you talk about virtual shorts only in op amps. Now that's because the value of A0 that you can get in op amps is very large. It's in the many thousands at least, whereas the value of GMRL you may get with transistor circuits is not so high. It may be modest, more like 20 or 30 or something like that. But it is still true that if GMRL does tend to infinity, these two nodes will have the same voltage and the gate becomes virtually shorted to the source. Okay. Okay. So if the transistor is in negative feedback, then there will be a virtual short between gate and source. Now this is also a useful way of quick analysis of circuits. Okay, in this case, for instance, if you didn't know the circuit before, if you didn't know that it was a source follower, but you did recognize that there is feedback for the transistor. Okay, how to recognize it is another question. I'm not going to deal with that here. So if you do that, then you can assume a virtual short between the gate and source, then clearly Vout becomes equal to Vi. Okay, and the same thing goes for all other control sources. Just as another example, I'll show the voltage controlled current source whose incremental picture looks like this. We have the load over there. This is GM VGS and this is VGS. Okay. Now we have already evaluated that this current I0 is Vi times GM by 1 plus GM times R, and it's approximately Vi times 1 by R if GMR tends to infinity. Okay. and you can also evaluate it in terms of the VGS. Okay. Now if you assume that there is a virtual short between gate and source, what happens? The source is virtually shorted to the gate, so the voltage at the source is Vi. The current through this resistor has to be Vi by R, and exactly the same current flows to the output. Okay, there is nowhere else for it to go. So if you assume a virtual short here, you will immediately see that the current here should be Vi by R. And of course, in a real transistor, there won't be a virtual short because GM is finite. So this current will be close to Vi by R. Exactly how close is it to Vi by R? That depends on the actual value of GM times R. Okay. Just for completeness, let me put down the expression for VGS. The expression for VGS in this case, you can work out. It turns out to be Vi times 1 by 1 plus GMR, which goes to 0 as GMR tends to infinity. Okay, and exactly the same happens in a current controlled current source as well as a current controlled voltage source. So if you want to evaluate all these negative feedback enabled control sources with GM tending to infinity, it's very easy. You just assume a virtual short between gate and source. It also gives you the approximate value of the transfer function as well as the input and output resistances. Okay. Now you have to put down the entire circuit and analyze to get the exact values. The reason this is used more often with op amps is that the gain of the op amps as such is very high, whereas these numbers like GMR that you get in single transistor circuits is not very high. Okay, but the same principle applies. Now what does it mean for the complete circuit? Let me put down again the complete circuit of the source follower, including biasing. This is connected to some supply voltage VDD. Okay. First of all, the bias point gets established, and there is negative feedback for biasing itself. That is, if the actual drain current is more than this current, the source voltage will increase, the VGS will reduce. Okay, and eventually this operating point gate source voltage will settle to the threshold voltage plus square root of 2 I naught by mu n Cox W by L. Okay, and let me call this C1. Now what happens when you apply a signal Vi? We evaluated that in the incremental picture VGS equal to 0 if GM RL, I didn't show RL here, RL will be there. As usual, capacitors are shorts. If GM RL tends to infinity. So the incremental VGS is 0. What it means is that the value of VGS will remain the same, and it will be the same as the operating point value even when you apply the signal. Okay. So for instance, let's say the difference between these two was 3 volts. This number was 3 volts. Then even when you apply the signal, this remains at 3 volts. Okay. So that is the virtual short. Incrementally, it is virtually shorted. In the total picture, VGS will remain constant. There is no incremental VGS. So this Vi, whatever waveform you apply here, will appear here as well with some level shift. That is, it will be lower, it will be shifted down, but the shape will be exactly the same. This is another reason why people called it a source follower. The source follows the gate voltage. It's not the same. There is a difference of 1 VGS between them, but it does follow the variations of the gate voltage. Okay.